explanation that made sense. I'm sure it's in somebody's best interest. And ostensibly yours. So, rotational inertia, also called moment of inertia, that's the term I'm going to use the most, is a rotational version of mass. So instead of mass, we're going to be using moment of inertia in calculations to talk about how easily things are twisted or stopped from twisting. Whereas mass and ordinary inertia cause resistance to linear acceleration, an object's moment of inertia describes its resistance to, you could say, like twisting, turning. I'm going to write rotational acceleration. Or no, I'm going to write angular acceleration. So right now my angular acceleration is 0 radians per second, or my angular velocity. And if somebody came up here and spun me, they'd have a hard time because I have a high moment of inertia. They wanted to get me going at a high rate. The rotational inertia of an object depends on both its mass and the distance of the mass from the object's axis of rotation. So this is what I was trying to demonstrate with the meter stick and the weight on the end of it, weight on different ends. As an example, consider a door. If the door's mass is increased, it will have a blank resistance to rotational acceleration. So if we make the door twice as heavy as it is now, keeping everything else the same, will it be harder or easier to open and close? Harder, because it's got more mass, and to get it moving, it's going to be harder, so it's going to have a higher resistance to rotational acceleration. And if moment of inertia is a measure of resistance to acceleration, what does that do to the moment of inertia? If we make the door harder to accelerate on its hinges, what are we doing to the moment of inertia? We're making higher. So moment of inertia is how hard it is. It's directly proportional to how difficult something is to accelerate. It's proportional to its inertia in a rotational sense. So I'm going to point over, let's see if I can rotate this thing over to the door. How many moves will that take me? Okay. So what we were just saying is, really is there any net torque on the door right now? Net torque, yes or no? Right now, is there a net torque? Yeah. How can you tell there's a net torque right now?
It starts moving?
Yeah, it starts moving this way. So looking down at the floor, there's this clockwise torque acting on the door. Now there's not. So I think I hear it going. I think there's a spring in these hinges. I think there's spring hinges, so they won't just stay open. Either that or the whole thing's leaning. But there's a torque this way. When it gets to this point, there's a torque the other way. There's no net torque. It's not accelerating anymore. So if we didn't have those, come on in, Malks. If we didn't have those springs on it, even a baby could open the door. Just if there were no springs or anything, it was perfectly balanced, even a baby could open the door with a finger. True or false? If there's no friction, it's not latched. But would they be able to open it fast? No. And if you made this door super, super dense, like a big giant bank vault door, could the baby still open it if there were no friction in it? Yeah, but it would be a lot slower. So having more mass in this is going to resist angular acceleration. Alternatively, this is the next part. If I took a bunch of the, bless you, if I hollowed out this side of the door and I took that wood and I compressed it into that side of the door, I took a bunch of the mass from far from the hinges and I shifted it over close to the hinges, would that make it harder or easier to do this?
Easier.
Easier. And if I took a bunch of mass and I put it there, then that would make it harder. So this is just demonstrating sort of an intuitive look at the moment of inertia formula. So the moment of inertia of this door is the mass of the door multiplied by the radius to that mass. And the way you would calculate this is you would take all the little points of mass in the door and you would multiply the amount of mass times that radius squared. And you would do that for every little bit of the door. If we put all the mass over here, then we would have a bunch of m times r squareds with very little r's. So you'd have very little inertia. And if we put all the mass over here, we get something different. So it's kind of, I won't say it's the average position of all the mass, although that might be right. I'm just afraid to say that because I'm not sure it's totally right. So let's go to, I've lost, oh, left some over here. Lost my notes. 10 minutes. So what goes here? If the door's mass is shifted inward so that it's closer to the axis of rotation, the door will have a blank resistance. Higher or lower? Lower. And that means that the moment of inertia will be higher or lower. Still a tricky one for people. So resistance and moment of inertia they go hand in hand. If you have lower resistance, you're going to have a lower moment of inertia, and vice versa. Bless you. If the door has a lower moment of inertia, it has less resistance to acceleration. So this next part says, starting with Newton's second law, basically derive Newton's second law for rotation. That's what I'm going to do here. Sorry about this. Talk about rotation. Hold on. I'm going to tighten my screws. Okay, so what's Newton's second law? Anybody? Trivia question? Newton's second law? There are 3 laws. You know the third one, right? So, what's the second? Nope, that's the first one. Force equals mass times acceleration. F equals ma. Okay, so I'm going to turn this into the second law for rotation. So instead of force, what am I going to want here? Torque. Torque needs to go there, but let me do some work over here. The relationship between torque and force is torque equals force times radius. So what does force equal? Take this equation, isolate force, what do we get? Torque over radius. So torque over radius is force. So I'm going to put that in here, torque over radius. And I'm going to leave mass alone, but I'm going to substitute in the angular version of A. So linear acceleration A is equal to what in the angular world? What's the angular symbol for angular acceleration? Alpha. So A equals alpha r. So instead of A there, I'm going to write alpha r. And now I'm going to multiply both sides by r and then reorganize some things, and I get torque equals m times r squared alpha. And this is the moment, bless you, of inertia. That's the simple formula for calculating the rotational inertia of an object. But we don't write it that way usually, unless it's convenient for some sort of calculation. We write torque equals I alpha. So I is the moment of inertia. And moment of inertia on a really simple scale is something's mass times its distance to the fulcrum squared. Bless you. Compare them. So Newton's second law is F equals ma, and the rotational motion version is torque equals I alpha. Two different definitions of torque, Mr. Pennington, just means now we have 2 formulas for torque. One is the one we just came up with, torque equals I alpha, which allows you to say, if I exert a torque on this wheel and I spin it, and I calculate what the acceleration was and how much torque I applied, I can plug in the acceleration and the torque, and I can find moment of inertia that way. Or that's how those 3 things relate. What's the other formula for torque? The first one we learned. Force times radius, or radius times force. Okay, rotational inertia of various objects. I'm redrawing now what I drew on the board right over there. So for a single point mass, I equals mr squared. And that would look like this. Here is a single point mass with a mass of m, and the radius is r, and it's rotating around this axis like so. With multiple ones, it's the sum of all that. I don't know. That's the notation Mr. Pennington used. But basically, you would look at each little bit of mass and look at what the radius is. And then you would find other pieces of mass in the same object, and you would look at those radii. And you would do this for all of them. So basically, mr squared for every little point of mass in the thing. And then you come up with the total, and that is the moment of inertia. So if you had 4 objects attached to a rotating stick like I'm drawing here, you could just do mr squared for this one, plus mr squared for that one, plus mr squared for that, plus mr squared for that. And for certain kinds of regular objects, somebody has done this. I'm presuming they use calculus to come up with these formulas. So if you, let's look at here's a solid sphere compared with a disk. And they're spinning around like this and like this. Which one has a greater concentration of mass close to the axis? The disk or the sphere? Look at how the mass is distributed here. Look at how it's distributed there. Which one of these has a higher proportion of its mass close to the axis? Which one's thickest at the axis is maybe another way to say this. Yeah, so if you start at the axis and you go out, this one's equally thick the whole way. But if you start at the axis and go out with the basketball, it's this thick and it tapers off. So which one's going to be easier to turn? The one with more mass toward the outside or the one with more mass toward the inside? Which is easier to turn? Inside or outside? Inside. That's this. So this has a moment of inertia of 2/5 mr squared, so 0.4. This has a moment of inertia of 1/2, 0.5 mr squared. And that's because this has more mass farther out. This has more mass farther in. If you look at the thin hoop, does it have more mass close to the axis or outside? Outside. It's got the full mr squared. So all these are some multiple of mr squared. And the closer you are to having all of your mass out at some particular radius, the higher that is. So this is the only one that gets the full mr squared. Really quickly, let me start you off on the homework. The homework is number 3, 4, and 5. And as long as I've been here, there hasn't been a 1 and 2. So this is a typical one. Calculate the rotational inertia of a solid sphere of mass 5 kilograms, radius of 0.25. So you just refer to this table. You'll never have to memorize this. And it says a sphere is 2 mr squared. So I'm going to write I sphere equals 2, did I say 2? 2/5 mr squared. And then I just plug stuff in. So that's 2/5 times 5 kilograms times 0.25 meters squared. And I can't remember what that is, but I do remember the units are kilograms meters squared, and it's really weird. So that's easy. Number 4 is easy. It just asks you to use a solid cylinder this time instead of a sphere, so you have to look up a different formula. And then when you get to this one, it's a little bit trickier because you're solving for torque and